Okay, so now it is time to do weak bases. And the weak base problems are a lot like the weak acid problems. The equation might seem a little awkward to you at first, but realize that there really is not a lot to it. The biggest thing is, as you're reading the problem, is you have to identify whether or not you're dealing with what we call an acid, what we call a base, or what we call a salt. And we're going to get into salts later. Just so you know, salts will be ionic compounds. Salts will be ionic compounds. So you know how to identify an acid. An acid is something that starts with an H, okay, like the problems we were doing before. Those are acids. This substance, NH3, is ammonia. You may have already known ammonia to be a base, but we're going to see a lot more what we call organic bases, bases that are not your typical OH compounds. We know all our strong bases have hydroxide in them, but most of the weak ones do not. And so we're going to see a lot of different bases. Remember that a base is really defined as something that produces OH when placed in water. So I'll show you with this one how that definition still holds true with NH3, even though it doesn't have hydroxide in it. But when you're reading your problems, for now, you're going to look to see if your substance is an acid or if it's a base. Again, it's an acid if it starts with H. If it doesn't, it's a base. That pretty much is your rule of thumb until we get to salts, and we'll add that part in. So for weak base problems, again, you notice it's very much the same. The only thing we have here is what's called Kb, because we're dealing with a base now instead of an acid. Kb is set up the same way as all the other Ks. Products over reactants, coefficients as exponents. So it's the same old process that we've been doing. So we're going to take and put NH3 in our first box. Now, when you're writing base equations, you do have to include the water. Remember we talked about with acids, you could show the water on the reactant side if you wanted to, but you didn't have to. And so with bases, we have to. So we're going to put H2O as our other reactant. Now, what's happening here, just sort of on the side, you don't have to do this on your paper, but you can in your notes if you want, for this first time. What's happening here is bases are, another definition, I guess, of bases, or bases are things that accept H pluses. So what's going to happen is an H plus is going to come over from the H2O, okay? If NH3 gets an H plus, it becomes an H4 plus, right? It had 3 hydrogens and a nitrogen. Now it has 4 and an extra charge. So it becomes NH4 plus. And then think about what's left over with H2O if you take away an H plus. Remember, water is essentially made of an H plus and an OH minus. So OH minus is left behind. And that's how all base problems will work. Okay, so if you're ever having trouble with your base equations, know you should come back to this example problem and look at it. You've been given your base. You're going to move the hydrogen over from the water to the base, 1H plus. That will leave that new compound being everything plus that H plus, okay, just like we showed when we did conjugates, okay, because NH4 plus is the conjugate acid of NH3, although conjugates we don't really need to define in this problem, but you can definitely use them. And then OH minus as the other product. And this fact that it makes this OH minus is what makes it a base. Okay, and all of these problems will produce OH minus. Now, notice they want us to calculate the pH. We know that OH minus can ultimately end up telling us pH. So this box that I just boxed in right here is the one that we want to solve for. If I can find that, then I can solve using the system of equations that we've learned before on getting pH from OH minus. So let's look at our problem. We start with 0.15 molar of that. Now H2O is a pure liquid, so it's going to get crossed off. Okay, it's not part of the actual equation at all. Then you're going to go to, and I think I'm just now seeing that on your note sheet. I think I only gave you 3 columns. Hopefully you've drawn yourself in a 4th one. If not, pause it and go back and do it, please. The ions, of course, start as zeros. We use X's. We make one side positive and one side negative. So I'm going to make that side positive and that side negative, and combine. So 0.15 minus X, then we have X, and then we have X. Okay, so that part, the red part I haven't read there is nothing new to you. Now, we are trying to find this OH minus right here, concentration, and what other information we've been given is Kb. So let's go ahead and write the Kb expression. So Kb is just like Ka, it's just like Kc. It's going to be product concentration. X raised to the first power and OH minus raised to the first power. All over, remember we're not going to include water because it's pure liquid. So just NH3 on bottom. Okay. We're going to take that KB that they gave us in the problem, which was 1.8 times 10 to the negative fifth. You see that negative fifth on there? So that means that our trick is very much a possibility. We're going to do it and then do what I showed you in class. So let's go ahead and put X and X. And then on the bottom, we're going to do 0.15 minus X. And then we're going to make our lives easier because we can use the trick and get rid of where X is being added or subtracted to another number. We're going to cross multiply and then take the square root of both sides. And you end up with an X value of 1.643 times 10 to the negative third. Okay, 1.643 times 10 to the negative third. Now here's where we want to double check and make sure that our 5% rule is in effect. And this is what we talked about in class. This is how you make sure that the trick is something that you should have used. So you're going to take your X value, and again, this is just a check. You're going to take your X value and divide it by the original concentration in the problem. Now if you do that, I plug that into my calculator, 1.643 e to the negative third divided by 0.15, and then times 100, so it's percentage. You end up with about 1%. So because this thing only, that's the percent ionization, by the way, because this thing only ionized 1%, we're good. As long as it's less than this 5%, then our assumption of using the trick was valid. So we're going to go back up. Okay, so we have X there. So X is this value, so that makes it nice and easy. 1.643 times 10 to the negative third is that molarity. Okay, so that's the first part of our problem. Now they want us figuring out what the pH was. So I have the OH minus. Multiple ways to do this. You can do whatever way you'd like best. I'm going to use that POH equals the negative log of OH minus. So if I plug in my concentration here, I'm going to get negative log of 1.643 times 10 to the negative third. Okay, and then we get a POH equal to 2.784, like so. And then we're going to take that POH, and we're going to do pH plus POH equals 14. Remember, you have to write your equations out. I know it's a pain, but we need to be complete. So that equals 14. So pH, if I subtract over that 2.784 and round to 2 sig figs, I get a pH of 11. So that's pretty much how you do it. It was maybe an extra step from the last example of the weak acid problem because we had to actually do this part, whereas before we could just do a one-step pH into negative log of H+. But other than that, it's the same exact idea. You have to write your equation, to use the information given to solve for whatever it is that is necessary to plug in to then solve for what you're solving for. In this problem, it was about finding pH from KB, and really there's only two types of problems, finding pH from KB or finding KB from pH. So let's go ahead and figure out the second type, which is finding KB. See here it says calculate KB when given the pH. So here's the pH. Just like we said before, pH is always at equilibrium. That is a very important point. Okay, and again, it looks like you only have 3 boxes there, so you're probably going to draw yourself in a 4th box. Now, looking at this substance, you see that it is not an acid. It does not start with H. Okay, that's what tells you that it is not an acid. So then you're going to treat it like a base. So we're going to put C10H15ON plus H2O. You might pause the video now, see if you can write the rest of this so you can see if you're understanding. So what I'm going to do is I'm going to take, because it's a base, I always transfer an H plus to the H2O. From the H2O, I should say. The H2O gives an H plus to the base. So to write this, I'm just going to shove that extra hydrogen onto the end. Okay, so you see how I wrote it there? Some people will do this. See how there were already 15 H's? So they'll say 16 and then do ON and a plus charge. Remember, the charge is very important, the extra hydrogen is important, but it doesn't really matter where you put it. You guys are not organic chemists by any means, so we don't have to be terribly particular with that, just as long as there's a H plus on there. And then remember, H2O, when you take away an H plus, becomes OH minus. Okay, so very, very important part of this process. And since you have to write these equations yourself, it's important that you know how to do that. Okay, so if that's still confusing to you, I suggest you go back and rewatch this part, and maybe go back and rewatch the part of the first example problem. Okay. Next thing we're going to do is cross off this column, and we're going to plug in the initial concentration of our base. Our ions will always start as 0 for these problems. We have X, we have X, we have X. I'm going to make this side negative, this side positive. This will be X and X, 0.035 minus X. And then, okay, so that should be it for that. And then we're going to take and figure out what we need to do to solve here. So we've used this piece of information. They've given us the pH. If they've given us the pH, we know pH can lead us to things like POH, H plus, OH minus. So let's think about what we need here. We know we need to solve for these, which means we need to know what X is, essentially. And if you look at this box right here, we know we can find OH minus from the pH. So let's take a look at how we would do that. So pH is equal to, well, let's see how I want to do this. There's a bunch of different ways to do it, but let's do it this way. And again, if you chose to do it a different way, if you'd already completed this problem before watching the video, that's totally fine. As long as you get the right answer, any system is fine. So 11.33 is the pH, and then we're going to subtract that. So the POH ends up equaling 2.67. Okay, so that's the first part. So now I have the POH. I can't plug that in over there on the table, though, because I need OH minus. So now I'm going to say, all right, that POH then equals the negative log of OH minus. So POH is going to be equal to, oops, we know the POH, don't we? So 2.67 is going to be equal to the negative log of OH minus. As we learned before, we're going to move that negative over and hit inverse log. So you're going to hit second button and then the log button and put in negative 2.67, and you get an OH minus of 2.138 times 10 to the negative third. Okay, so that's the concentration of the OH minus. So now we can come back up to the top here and plug that in. I know the OH minus is 2.138 times 10 to the negative third molar. Okay, but that's still not our final answer because they want KB. But what that just told us is what X was. If we found OH minus has represented by X. So I now know that this is 2.138 times 10 to the negative third molar. And then I can do 0.035 minus that, comes out to be 0.03286 molar. So now I have my concentrations, so now I can write my Kb. So Kb is going to be the concentration of the products, C10, H15, ONH plus, times OH minus. You're going to see some really weird looking bases in this chapter. Really weird, don't worry about it. There's a lot of weird stuff out there. Okay, then you're going to plug in your concentration. So we're going to have Kb equals, you can just put, see how both the top numbers are the same? If you want to save yourself some writing, you can just do it like that. So both of these means the same thing as squaring it. And then 0.03286. Plug everything in, solve for Kb, and round it, and you get 1.4 times 10 to the negative fourth. Okay, so same process, a little bit of extra steps in there because we're dealing with a base. We have to do some extra stuff with some conversions, but really the same